Hello, everyone. It's great to see you. Thanks for coming. I hope last week's filming wasn't too distracting. The original plan had been just. I thought they were just going to interview me after the talk. I think they came and they saw how nice the space was and how nice all of you looked, and they wanted to get some shots of the lecture as well. But today it's just us, so I can speak freely. Good. And well, first let me remind you. Last week we talked about in the hot, dense early universe, you go from some charged plasma when the temperature is cool enough. You do some initial nuclear fusion. You form some helium nuclei. At even lower temperatures, we get recombination to form atoms. The universe is now neutral, and photons can free stream through the universe. Those formed the cosmic microwave background, which we observe today. And we already saw from the inhomogeneities in the cosmic microwave background that we needed dark matter to account for the size and the spectrum of over and under densities in the cosmic microwave background. Now, today I'm going to continue playing the story forward. It's going to be somewhat of a hodgepodge of things, and I should disclaim in advance that we're going to get to things that I'm not an expert in. There are other experts in the buildings here, but what do I want to say? Yeah, so some of the things that we're going to get to: stars, supernovae. There are many other experts here. Good. And I wanted to say, in general, well, it's been true throughout the lectures, but it's going to be especially true today, that there are things that I'm going to spend one slide on that really could do with their own full Compton lecture series themselves. And I think, in fact, some of these particular things I'm going to get to have been talked about in Compton lecture series in the past. And I'm sure as research progresses, they'll come back up in the future. But also, in exchange for some of the things, as I play the universe forward, I'm going to get to things that are outside of my domain. I am, just to remind you, sticking to the schedule I had set out originally. So next week, we're going to get to things that really are the sort of thing I think about for research. We're going to get next week to beyond the standard model of particle physics, to think about physics at even smaller scales and even at earlier times than we've seen today. Okay, but let me jump in. First, remind you the cosmic microwave background. I can't show this picture often enough. This is the data from the Planck telescope, 2013 or so. Absolutely remarkable high-definition image of what the universe looked like at around 380,000 years after the Big Bang, some 13.8 billion years ago. And again, our question is, going from this nice picture of the universe at very early times, how do we get to what we see today? Well, what do we see today, first of all? Another really fantastic image that, and my caption has been cut off, and is it too bright? Maybe. There we go.
Here we go.
This is always a bit dangerous.
Oh, no, you did good.
Oh, wonderful. Should I do even more?
Hey.
Oh, that's great. Okay. Okay, so this is the Hubble, a Hubble Deep Field image. Perhaps you've heard the story of this before. I just wanted slightly lower lighting. Okay. Yeah. Either way. Good. So Hubble is this fantastic telescope that we sent to space. You've probably heard of, taking these amazing images of all sorts of objects. And the story of the Hubble Deep Field images is that the astronomers suggested something a bit crazy. They had to fight for this proposal. They suggested, rather than pointing Hubble at Andromeda or at some interesting star that we see in our galaxy or some nebula nearby, they said, let's point Hubble at a small patch of apparently entirely empty sky, right? So they pointed Hubble for a long time at a small black spot of sky, incredibly small really. If you put a grain of sand on your finger and hold it at arm's length, that's about the size of the spot where they were looking, but they integrated, they pointed at that spot for a long time so they could collect many photons from it. And to our amazement, it's beautiful to see, let me say at least, that indeed, when you look very carefully at what just appears to be a very small black spot of sky, you find that there are tons and tons of galaxies out there. This incredibly tiny region of the sky, in fact, contained roughly 3,000 galaxies that Hubble was sensitive to, that Hubble could see just in this image. So there's an enormity, well, just to get across the enormity of what we have to explain. 3,000 galaxies in one region of the sky, that's about 1 in 20 million, so 20 million such regions in the sky. And just from this image, it just seems like sort of chaos, there's stuff all over. How do you ever understand any sort of order to such a thing? But if you look even more carefully, Hubble was in the this I think was in the mid-90s. If you look even more carefully, this is a survey done around 2000. And this is another of these maps of the sky where they've projected everything onto an oval. The plane of the Milky Way, our galaxy, is in the center, and there's a bit of color coding by distance. This is an all-sky map at a particular redshift, looking for even more galaxies, although not as deep. It doesn't see as faint galaxies as Hubble does, but they wanted to see everything all over. These are sort of the trade-offs of doing astronomy. Look at everything or look at one thing very deeply. And they can find that there is some sort of structure here. You see sort of linear features of clusters of galaxies when you look on large enough scales, and there are a bunch of named sort of things, named features, clusters, superclusters, labeled in this image. So this is the sort of thing that we want to explain. And in general, this is the theory of structure formation. We saw at 380,000 years after the Big Bang, we have the cosmic microwave background, we have these very small inhomogeneities, but there's still, that's just a snapshot of what things look like at that time. There are still, this dark matter then continues to form larger and larger gravitational wells. Recall, the dark matter can more easily form gravitational structures, fall into places where there are overdensities because it doesn't have the pressure that standard model matter has. It just falls into some region of heavy gravity. And now, if I want to use the board, I'm going to, okay, good. Okay. Good. And one general thing I want to say, and because I haven't emphasized this before, is that often in research in physics, in research in lots of areas, when one is studying complicated enough systems, it is very difficult, if not impossible, to write down an analytic solution for the system. Right? We in the first part of the lectures, I set up the problem of the hydrogen atom and understanding it quantum mechanically with the Schrödinger equation. And that is a system that is simple enough that we can just solve it by hand. But very frequently, when you have more complicated systems, like, well, you want to understand the structure of DNA or some proteins, or you want to understand the structure of all of the galaxies in the universe, that you can't, with a paper and pencil, solve all of the different, very complicated differential equations governing the evolution of these systems by hand. There's a lot that we can understand analytically, but often we need to numerically solve, to put the system on a computer to see what really happens. And this is an important feature for especially theories of large-scale structure. Although we do understand a lot analytically, it is useful to run it is useful to run simulations. Good. Good. So again, what they're starting with here are just this is a simulation that only includes dark matter. What they're starting with, now the light should go back down because I decided not actually to write anything down. Wonderful. What they're starting with is a map of dark matter with slightly less and more dense regions as informed by our picture of the cosmic microwave background, and then we understand the equations of gravity, Newton's laws, general relativity, and so they can play that forward to see what further gravitational gravitational clustering happens. And so you can see, okay, it's going a bit quickly, but regions in which there was initially some small overdensity attract more and more dark matter, and you end up forming these filamentary regions, right? You can see some sort of linear structures. You might have seen some popular articles about the cosmic web. This is what that's referring to. The color is just how dense these regions are, and they're color coding where you expect. The simulation, I think, only includes dark matter, but it is the case that you generally expect galaxies to form at these regions that first have been made very dense by dark matter. So that's some of this coloration you were seeing. So they were doing some evolution. Now they're playing some sort of zoom through to see this really is a three-dimensional simulation of the structure. You see lots and lots of regions where filaments have intersected. Good, yeah, so the main sort of feature is some, where's white? Someone has taken, her. Yeah, again, great. Okay, that's not what I wanted. Maybe it is what I wanted. I don't know. Okay. But again, you'll see the development of these sort of linear features known as filaments. We have some understanding from fluid mechanics why you tend to find some sort of linear features, and at the regions where these intersect, you have enormous, and these are features again in the density of dark matter, and at these regions where these filaments intersect, you have an especially large density of dark matter, and you find that these then attract, again, it's easier for dark matter to clump, to fall under gravity because it doesn't have any pressure pushing it apart. But when you form these very large, dense regions of dark matter, then they also attract normal baryonic matter, hydrogen, helium, standard model stuff, and you find large clumps of galaxies at these regions. And I think I had another, oops, there we go, another one to show just for some complementary viewpoint. Great, I should have prepared this in advance. Okay, again, now this I think, really things are a bit complicated. All of the time scales are intertwined for the formation of structures of dark matter, these cosmic filaments, and the formation of stars, which we'll get to in a bit. So really, this is a slightly more detailed simulation where they're including dark matter and also some of the effects of regular standard model matter, most importantly supernova, which we'll get to later. Supernova are enormous explosions that, because of the extraordinary amount of power they produce, it's an explosion of an entire star, they can also shape the formation of galaxies. Okay, now we're focusing in on one sort of galaxy here. Yes, a question.
Could you give us some sense of time?
Yeah, sorry, good. So this is happening, this is over the entire lifetime of the universe. So something like 10 billion years.
Good.
Good. And actually that brings up an important point as to how we're going to study these things, which maybe I should remark on. Indeed, in cosmology and in astrophysics, the timescales are incredibly long. It's going to take hundreds of millions or billions of years for galaxies to evolve, to form. It's going to take millions of years for stars to live their lives, to evolve. And so, indeed, you can't look out in the sky with your telescope and watch a galaxy form, right? But that's just in the same way that if I wanted to understand human aging, I can't look at one of you for 10 minutes, or even if I looked at you for a day, a week, I wouldn't be able to understand very much about human aging. But if I looked at, say, everyone on campus today, right, and compared everyone over a short period of time, then because I have a large population of people at different stages of aging, then I could understand something about how humans evolve, throughout their lives, by looking at lots of different people. And in the same way, we can understand something about the evolution of galaxies by the fact that Hubble image that I showed has, let me pause this, has indeed, we have samples of, this image itself has 3,000 galaxies. We have samples of hundreds of millions, billions of galaxies that we can look at. So the other important fact is we are lucky that we have a finite speed of light. Light takes some time to travel, so by looking out in the universe at different distances, we also see galaxies at different times of the universe. And so by understanding the population statistics and looking at many, many, many galaxies, we can understand how they change over time, how they have changed over time, even though, indeed, because the timescales are ridiculously long, we can't look at one and see it aging. Good. No, I think it was a good aside. Yes, thank you. Yes.
Are the rotational axes of the galaxies along those filaments, are they aligned? Is there some sort of a pattern with the rotational axes and the galactic structures or groups?
That's a really good question, and I bet someone in that building knows the answer, but I don't. I would expect so, but actually I don't know. But that's a great question. Good. Oops. Wait back. Okay. Good. And indeed, perfect. You set me up perfectly. I don't know why my slides are being cut off. But indeed, we can go and look. Now this is an even more modern, the Sloan Digital Sky Survey, I think a decade or so ago, went and tried to catalog way more, tons and tons, something like 200,000 galaxies that we could see. And one of the great things about the Sloan Digital Sky Survey is that it could also look at very distant galaxies that were point faint. And so this is a plot. We live here this is again, well, what do I want to say? This is some slice of the universe looking out from where we are here, back at more and more distant galaxies in this region, in this slice of the sky. Again, when we're looking at more and more distant galaxies, we're looking farther and farther in time, and you can see already from this image that there's some sort of structure. It's not entirely homogeneous, right? There isn't like a constant density of galaxies everywhere, but indeed there are some features, some lines, there are some voids, some spaces where there are not many or any galaxies. And let me say, this is quite nice because this also compares, so these are galaxies going back in distance, which is also going back in time. I've forgotten. Aha! Good. And this also compares, here we have the plot of the cosmic microwave background, again, with some cold spots, some regions of lower density or higher density, and you can compare directly which regions of the universe have more galaxies, have more structure today, or along this line of sight in the past. You can compare directly to those overdensities and underdensities in the initial cosmic microwave background. Sure, quick question.
The scale here.
Yes.
2, 4, 6, 8, 10.
So this is billions of years in the past. Yeah.
Millions of years there. Is that the center over there?
This is the center, meaning just where we are. So there's no really special point, but of course we're observing from where we are. So we can only see out.
Could we be at the border instead of the center?
No. Each one of us is at the center of our own universe, in many ways, but also physically. No, of course. So these are some observations. So of course the observations are all going to be made from Earth or very near to Earth. So indeed we can't. We can only infer what someone very distant away might see when looking back at us. But we make these observations from Earth, looking outward into the past because of the finite speed of light. And let me, in fact, zoom in on that central, on the region closer to Earth, so you can better see. Indeed, there are structures. There are voids where you see very few galaxies and filaments. Good. I should just write void. What? I've lost the. Good. Void. Okay. Great. That was worth it. Perfect. Good. And in fact, if you zoom in even further, you can see much closer to us very well that there is structure. There are these cosmic filaments. Okay. Good. And just to reassure you that we're doing things not just by eye, but really quantitatively, like before when I showed the power spectrum of the cosmic microwave background, the power spectrum, which was, comparing our theory of how big the inhomogeneities in the cosmic microwave background were with what we actually saw, the data. Again here, we can understand, even without numerics, in some very nice analytical frameworks, effective field theory of large-scale structure, we can understand with this black line what the sizes of things should be, how big. There's lots of structure on all different scales, right? From us to stars to galaxies and clusters of galaxies, and you can understand what that. How much structure on different scales there should be, and indeed we have a good match with our data from lots of surveys of galaxies and other forms of large-scale structure. Good. Okay, but at that same time as the large-scale structure is forming as galaxies are forming, primarily from the gravitational collapse of dark matter, there is this other effect from standard model matter. Maybe I'll go back to a little bit of light. And it's really from the perspective we've gotten to this, starting with, in the first part of the course, the structure of the standard model and finding this very simple understanding of particle physics with just a few particles controlling everything, comprising everything around us. It's really amazing that this phenomenon of stars exists at all. But what happens is, just like in the cosmic microwave background, again, we saw these inhomogeneities where, in fact, the size of them was controlled by dark matter. The standard model matter follows those regions of higher and lower densities, collapsing more in the regions of higher densities. But whenever you have some, this is horrible. Whenever you have some overdense region, fine. Whenever you have some overdense region, indeed, standard model stuff feels the force of gravity and wants to collapse. Now, always, it's the case, I already regret that. Always, it's the case that there is pressure in standard model stuff. Unlike the case of dark matter, where dark matter barely interacts with itself, so gravity can just compress it as much as you want. For standard model stuff, like we talked about, standard model stuff interacts with itself. And so compressing it, just like in chemistry, there's a pressure that makes it difficult to compress. So there is pressure that fights against the collapse under gravity. Okay, good. I'm just redrawing that picture mostly. Pressure, gravity, fine. Good. Now, when we discussed it in the cosmic microwave background, all this did was make it more difficult for standard model stuff to be compressed. Standard model stuff has this additional pressure fighting against gravity, so it doesn't fall into gravitational overdensities as much as dark matter does. Its collapse is slower than that of dark matter. But now, in the later universe, there is a new sort of phenomenon that occurs. Because when these overdensities have grown large enough, the temperature in the center of these stars can again, because now we're going later and later in the universe, you're getting larger and larger overdensities, higher and higher densities, and when the standard model stuff falls into these regions, the temperature gets larger and larger. The benchmark, was something like a billion degrees Celsius. The temperature gets so large that you have a new phenomenon where in the center of these stars, you can have, nuclear reactions again. The universe has not seen nuclear reactions since Big Bang nucleosynthesis, a few minutes after the Big Bang, right? And that turned off very quickly. We got some helium atoms, but otherwise the nuclear reactions turned off very quickly because the universe was cooling and expanding. But another 100 million or billion years later, we again have some nuclear reactions that can occur when you start having regions that are very, very dense, okay? And these nuclear reactions that occur at high enough temperatures, the primary one in relatively low mass stars, like the sun, is known as the proton-proton chain. What do I want to write? What this does is it produces energetic. What should I write? Any of those? Okay. It's mostly this. E plus helium. Okay. So what you have, and then more, as shown on the slide, you produce lots of very energetic photons. Good. Okay. So now, again, when things are dense enough, you can have nuclear reactions occur, nuclear fusion occur. It happens in a different way than it did in the early universe, because in the early universe we had all of these protons and also all of these neutrons, so they could form deuterium relatively easily. Here, well, in a different way, let me say, here we just have mainly all of this hydrogen gas that has been falling into these dark matter overdensities. But you can fuse two protons into a deuterium. That's what that should be. Deuterium. Sorry. Good. You can fuse two protons into deuterium, and again, with more and more hydrogen nuclei, more and more protons, fuse them into helium. And helium, because it has a larger binding energy, helium, the production of helium results in lots of energy being carried away by photons and by positrons. Okay? So it's not just, it's no longer just the pressure of trying to compress a box of gas where you just have, there's some challenge to compressing it just because there are all of these things interacting and trying to move everywhere, but you in fact have a new phenomenon, a new source of energy that occurs when you compress standard model stuff tightly enough, a new source of energy from nuclear fusion that provides additional pressure that doesn't just it doesn't just slow down the gravitational collapse of this region, but really stops it for a long time. This is the phenomenon of stars, right? A star like the sun is not collapsing, even though it has enormous gravity, because in the center of a star, and in fact, I think in the center of a star like the sun, there are these nuclear reactions going on, turning hydrogen nuclei, protons, into helium, which produce tons of photons, which travel outwards and result in additional pressure that stops the process of gravitational collapse. Okay? This is a really remarkable phenomenon, again coming from the structure of nuclear physics. If you just had in some theory of matter 150 years ago, where protons were really things which were fundamental and point-like, and we didn't understand nuclear physics yet, we couldn't understand how stars were stably forming and living for millions of years. It's something, again, that depends on the detailed particle physics going on in our universe. The fact that there is this rich structure of nuclear physics allows for these reactions which result, which are at play in the large-scale evolution of the universe and of enormous objects like stars. Okay. Yes?
Since dark matter doesn't have that pressure, doesn't fuse and have anything to counteract gravitation,
Yes.
what stops it from forming black holes?
Good. Indeed. Sorry, let me just think about what I want to say. Indeed, you can form black holes from gravitational collapse. The barrier, the barrier is that it's difficult for dark matter to lose angular momentum. What do I want to say? So in addition to, we've talked about energy conservation. There's another quantity called momentum, which is conserved, and in fact, angular momentum. Perhaps you've seen demonstrations about this. You can think about a ballerina. What do I want to say? What do I actually want to say? In order to get extremely dense regions, particles sort of need to shed some of their angular momentum. And standard model particles can do this by emitting, say, photons. Standard model thing can emit a photon which carries away some of its angular momentum, and so brings it sort of closer to some central object it is rotating, and that's harder for dark matter. But it's true that indeed, good. Some of the black holes that we know about form from the endpoints of stars. That's very much a process involving standard model matter. But in fact, it's also the case that at the center of more or less every galaxy, we've now discovered that there are supermassive black holes located at the center of galaxies, like our own has a supermassive black hole known as Sagittarius A star. And indeed, those black holes very likely are formed as a result of the fact, as you say, that for dark matter there is not this humongous barrier to gravitational collapse. Okay, and as I sort of failed at waving at in detail, it's quite complicated. There are many things going on, but indeed, the fact that dark matter can form gravitational structures quite easily is likely what has resulted in these enormous black holes at the centers of galaxies. That's very very true and a very interesting point. Yes, maybe a quick question since I'm. Okay, yeah, we'll talk later then. Thank you. All right. So now that we've
Okay, can I have a question here?
a quick one. I'm running out of time.
If all these stars shed light,
Yes.
that means they are losing mass.
Yes.
So they are shrinking. All the stars are shrinking.
In terms of energy,
And mass.
yes. Well, they can also accrete matter.
How?
Right. Oh, well, because there's still gas, all gas and dark matter. There's lots of stuff all around. So things are also falling into the say, sometimes an asteroid falls into the sun or something.
Is it an asteroid or they are sucking something from the dark matter?
Both. There can be lots of things. Dark matter, sometimes photons from other stars hit our sun, right? But indeed, when a star emits lots of light, it is losing it's losing energy, it's losing mass to outer space. That's definitely true. Okay, so now that I've said something about stars, I wanted to say, well, because I think it's of some interest. So last week we talked about the evidence for dark matter from the cosmic microwave background needing to get those inhomogeneities correct. And just earlier, as I told you, what's really driving those simulations and the process of the large-scale structure forming is, again, dark matter. And so we see it in the agreement between those enormous surveys like the Sloan Digital Sky Survey and what we predict from the large-scale structure in these simulations say. But in fact, historically, the existence of dark matter was first inferred by looking at the speeds at which stars rotated around different galaxies. Let me again turn this off, down a little. Good. So here, good. Here on the left, we have a simulated galaxy without dark matter. On the right, a galaxy with dark matter. And the effects of dark matter, because dark matter, well, because of this fact I didn't really explain very well that dark matter has a hard time losing angular momentum. While galaxies have both regular matter and dark matter, as you know, the regular matter is sort of distributed in a disk. Well, for disk-like galaxies, let's say, like the Milky Way, right? There is this sort of flat plane in which mostly the galaxy lives. The dark matter, by contrast, because it doesn't have the same sort of interactions, let me play this again, the dark matter is distributed sort of spherically around the galaxy. It doesn't collapse to planar structures. And so it gives a different sort of mass distribution if you include the dark matter, and that leads to different sorts of velocities for the stars that are orbiting in the galaxy. Good. Here more quantitatively, this is one particular spiral galaxy, Messier 33. And if the only stuff that was there was the visible stars and gas, standard model sorts of stuff in this galaxy, then good. Then you could infer just from what you see what the gravitational potential is, what the mass distribution of this galaxy is, and then you can compute from gravity. I think really this mainly just needs Newton's laws, although you also use general relativity. You can compute what you would expect, the velocities of stars you would expect for that mass distribution. And you find, people found in the early parts of the 20th century, Zwicky is often credited with the first such observations. People find that the velocities of stars do not at all match what you'd expect if the mass distribution was only from the standard model stuff like stars. But in fact, there must be lots and lots of dark matter in these galaxies as well, which are responsible for, well, a deeper gravitational potential well, which causes stars to move more quickly when they're orbiting the galaxy. Now, I wanted to say this because historically, this was the first evidence for dark matter. In fact, I think the evidence from the cosmic microwave background is even more compelling and makes it more obvious that dark matter must be some sort of particle as opposed to other sorts of exotic ideas people proposed in the past. But I thought it was useful for me to show this as well.
The galaxies are swallowing the stars, as you showed these two galaxies rotating, and all the stars are going there.
No. The galaxies are composed of stars. What you see when you look at a galaxy rotating, that's the stars.
But it shows that they are gravitating toward. Do you want to put the two galaxies that these two.
Sorry, this is just
blue-
one galaxy. These
No,
are two different
the blue-
models for what's happening in the galaxy.
The video of the two
Ah.
blue galaxies that you showed.
Yes. Sorry, the question is,
And here,
yes.
it seems that the stars are going inside the galaxies, inside the center.
Oh, good. That's
So
indeed true.
it is the center that's swallowing the stars?
Oh, good. So just like just like in the solar system, the planets orbit the sun, which is the most massive object in the solar system, so the center of gravity, the stars and our solar system itself rotates around the galaxy. Indeed, in some good. The dynamics of the galaxy are more complicated than of the solar system. So indeed, you do have stars that go from outside in the disk to inside, sort of in the core of the galaxy over timescales of hundreds of millions of years. But mainly what you should think of when you see a galaxy is that all of the stars, all of the solar systems, are rotating around the center. But really, I mean, they're moving under the force of gravity. So depending on what the shape of the galaxy is, they can have different sorts of orbits. That's certainly true.
So stars are forming outside of the galaxies and then going inside the galaxies.
Yeah, we can talk more. We can talk more later. But I'd say stars form in the galaxies and rotate around then. Good. And in fact, with some maybe appropriate timing. Perfect. Here's a simulation which is looking more at a particular galaxy. Indeed, it's the answer is that it's complicated, and galaxies are not my focus of study, so I can't, and we don't have the time to go into everything in detail. But it is complicated. Galaxies, stars form in galaxies and orbit, but galaxies themselves indeed attract gas and dust and dark matter from the intergalactic medium, and galaxies can collide with each other. Our galaxy will collide with Andromeda in a couple billion years. Nothing for us to worry about, but there will be some interesting dynamics to observe in the night sky for our descendants a couple billion years from now. Good. All right, let me get back to, because I'm running out of time. All right, but okay, with stars, finally, with stars, we have some heavier nuclei. We have another chance to do nuclear fusion to build up heavier and heavier elements. And that's one of the big questions was how do we go from the early universe with just protons and neutrons and electrons to what we see today, our carbon-based life forms. So finally, we wait hundreds of millions to billions of years, and we have these regions of stars which can, we have some stars which can form and do nuclear fusion, finally. So we can think about producing the elements that make us up, but they're trapped. Whatever sort of nuclear fusion goes on to produce carbon, nitrogen, oxygen, all of these things that we care about, they're trapped in the center of a star. What good does it do us if they're produced out there, if they're produced in the center of a star? Well, thankfully, at the end of the lifetimes of these stars doing nuclear fusion, they do something fantastic and remarkable. Some of them, at least, can end their lives in what's known as a supernova. So, we talked here about fusing hydrogen, which is just the nuclei of hydrogen are just protons, into helium, ultimately. But eventually, the star will run out of hydrogen, And so that pressure from the nuclear reactions producing these very hot photons, pressure fighting against gravity, turns off. And then again, you have gravity win and collapse the star further. So you, but nuclear physics is very rich. Out of this very simple standard model of particle physics, the structure of nuclear physics that you get is very rich. So what can happen is the star collapses more, and the center becomes even hotter than this, and eventually, when it's hot enough, when it's become dense enough, now you can fuse the helium that you had produced from hydrogen fusion, you can fuse the helium into carbon. And there's a whole, a bunch of stages of this process where you, the center of the star, things collapse, the center gets incredibly, incredibly hot above the energy threshold that you need to do some sort of nuclear fusion. So again, you have some nuclear fusion process that is producing lots of energy. Again, this is first hydrogen fusing into helium, helium then fusing into carbon. Then you have this process of carbon fusing into carbon and helium fusing into oxygen, neon, magnesium, all the way, in fact, up to iron. When the center of the star gets incredibly heavy, incredibly hot, it turns out that iron has the most binding energy. Iron is the most stable, in some sense, nucleus. So you can only get energy from fusion by building things up and up, creating heavier and heavier nuclei up to iron. But at that point, because, and again, this curve is some emergent phenomenon from ultimately the standard model of particle physics, but it has this structure such that iron is the heaviest thing that you can produce by fusion to get energy, to get pressure that would prevent a star from collapsing. So once you start producing iron, you can't anymore do some nuclear fusion to prevent gravity from winning. And so there's another remarkable phenomenon which occurs, which is that, if you have a massive enough star, once gravity has won finally over nuclear physics, and you're producing iron, and that can no longer happen enough such that things are collapsing again, there can in fact be another phase transition to an even more exotic sort of matter known as degenerate neutron matter. I'm describing the formation of a neutron star, which I don't have too much time to get into. But what happens is, again, this is some emergent, remarkable behavior out of the standard model of particle physics. You go through all of these stages of nuclear fusion, and finally, the last thing that can happen is an even more exotic sort of phase transition to nuclear matter that again prevents the full collapse of the star, but results in a sort of bounce of the matter that wants to collapse and produces these enormous remarkable explosions known as supernova. This is a picture of the Crab Nebula, the result of a supernova that was observed, written about by the Chinese astronomers in almost 1,000 years ago, and now with Hubble we can observe it with remarkably high definition to see the eventual outcome of the supernova. And this very complex physics is what allows the large nuclei that are produced in the center of a star to ultimately leave and seed the next generation, seed the interstellar gas, intergalactic medium with heavy elements, so that the next generation of stars, and I won't, this is in French, so I won't play the sound. But they have some nice animation. So here we have what they're trying to show here is iron is finally being produced, and in fact this happens very quickly compared to the normal timescales of the star. But this is the very end of this star's life as at least a regular sort of star. Now you have things happening in very quick timescales. Iron fusion, or fusion to iron, has turned off, so the source of pressure is lost. You get some collapse of the star as gravity is again winning. And again, you have some exotic phase transition now to neutron matter at the center of a star, and this results in lots and lots of neutrinos being produced. These are the most energetic phenomena, more or less, known that occur throughout the universe. In fact, when one of these supernovas occurs, briefly, the one star that is undergoing the supernova is more energetic than the entire galaxy in which it resides, which has maybe 100 billion such stars. So supernova are incredibly energetic, and you get this remarkable phenomena where much of the outer layers of the star are sort of blown outward. Okay, now they're giving some analogy to fluid dynamics, which is interesting, but I don't. Let's skip. Yeah. Oh, okay, great. Good. So we understand. No. Good. So it is these supernova and other such phenomena that are responsible for seeding the galaxy with heavier nuclei. And in fact, now we understand to a very amazingly good degree what the astrophysical origins are of all of these sorts of elements that we see on Earth. Supernova are these exploding massive stars that indeed create many of the elements that we care most about. Depending on the mass of the stars, you can have different sorts of endpoints that have different, in detail, sorts of nuclear reactions. Let me mention, in particular, the most, this relatively complete understanding of how elements are formed really was only confirmed something like 5 years ago when using a gravitational wave interferometer known as LIGO, we observed merging neutron stars in neutron stars again are the endpoints of some of these supernova, and sometimes you can have binary stars that are both neutron stars and they merge, and those incredibly energetic collisions again produce lots of these very heavy elements. I wish I could tell this story in more detail. Maybe at a lecture, a Compton lecture soon, someone will tell that story. What I wanted to get to, because I had promised, is that by looking at supernova, in around the turn of the millennium, we found a remarkable surprise. Supernova, not in fact this type, another type of supernova, but another type of supernova, we understand very well what their energies, what their luminosities are, how many photons, what temperature they're producing. And so by looking at lots of supernova, you can measure quite precisely what the current rate of expansion of the universe is. And what we found in 1998 is that, in fact, naively, okay, we already figured out we don't have a steady state universe. We started with some sort of hot Big Bang and everything was moving apart. Now, naively, or your intuition about what should happen then is that, okay, everything is moving apart, but maybe at some point in the far future, gravitational attraction is going to win again, and everything is going to come back together and maybe eventually crash back into some sort of reverse of the Big Bang, a big crunch. What we found by looking at the supernova and carefully measuring their distances is in fact that's not the case. The expansion of the universe is not getting lower, but in fact accelerating. Into the future, there is more and more expansion of space over time. That's what all these supernova lines, these supernova data, slightly preferring this line with vacuum energy compared to, meaning accelerating expansion rather than decelerating expansion. Now we have, it's a bit hard to see in this, now we have even better data. This is from something a lot of Chicago astronomers worked on, the dark energy survey. Now we can see even better that all of these supernova, these red dots that we see, really do prefer this gray line where we have some additional component of energy, some dark energy at some time over this blue line where we don't have any dark energy today. There's some additional component of some additional sort of matter, source of energy, which is resulting in accelerated expansion of the universe. I'm sorry for going over time. If you had somewhere to be, I won't be offended. Just a few more minutes. So indeed, this was quite a surprise to most theoretical physicists and observational physicists. But indeed, it is the case that now the expansion of the universe is accelerating, and that does require that there is some other component of the energy in the universe which behaves a bit differently from the standard model and from dark matter. And we call this has the name dark energy just because it is also a sort of stuff that doesn't interact with photons, but I should emphasize, it doesn't necessarily have anything to do with dark matter. We have some theories about what this could be. It might be that there's a new scalar field, sort of like the Higgs, but that's responsible for this accelerated expansion. It might be that really we're just measuring the energy associated with empty space. In general relativity, there can be some sort of 0-point energy just of empty space itself, and this gravitates a bit differently than just particles, resulting in this phenomenon of accelerated expansion. And what? The important thing for me to say, maybe, is that this was is a remarkable thing to discover, and in fact changes what we think happens in the far future of our universe. If this expansion accelerates, rather than eventually turning around, well, for one thing, the galaxies Galaxies that are very close to our own, like Andromeda, as I mentioned earlier, we're eventually going to collide with Andromeda. We're so close that our local sort of gravity wins out over this expansion of the universe. But galaxies that are not part of what we call our local group, as space expands further and further, more and more, will get farther and farther away. They will be dimmer and dimmer, and in something like 1 trillion years, our descendants, well, for one, they need to move to a different solar system because the sun will be long gone. But assuming that our descendants live on somewhere in 1 trillion years, they won't actually be able to see these distant galaxies. If they have lost our observations from Hubble today, they won't be able to observationally confirm the large-scale structure of the universe. Everything will be too far away, too dim. So we're, in some sense, we're living at a great era, a great time in cosmic history where we can still see other galaxies and understand what the evolution of the universe looked like. Okay, and good. Just because, well, I want to eventually get. This was going from the very early universe to sort of to us, and I do want to remind you that there is tons more that I'm not getting to. That's also an incredibly interesting story. The solar system itself formed something like 4.6 billion years ago. As we were talking about today, our sun, our solar system, was not one of the very early solar systems because those stars only had the hydrogen and helium from Big Bang nuclear synthesis. But after some generations of stars formed and did nuclear fusion and went supernova, exploded and seeded the galaxy with these heavier elements, finally, some few billion years ago, our solar system formed and contained all of these heavier elements that make us up. And it's a remarkable story, something that really amazed me when I sort of grokked it relatively recently is, if you picture some idyllic natural environment on Earth, you think of, well, what do I want to say? It is a fact that dirt, soil, is wholly a biological byproduct, right? 4.6, 4.5, whenever billion years ago, when the Earth formed, what we think of as integral to what the Earth is, soil, was not present, right? The Earth at its formation was rock and some air that was nothing like the air we see today. There wasn't any free oxygen, some rock and air and water. And remarkably, it took some hundreds of millions of years, but that is nothing compared to the age of the planet. Remarkably, in only a few 100 million years, the chemicals dissolved in the early oceans had formed cells. Right? We know life formed remarkably quickly. As far as we can tell, only once, but it only has to happen once, right? And we have the whole planet, a huge volume of water. We can wait hundreds of millions of years. It only has to happen once that some of these molecules come together in a self-replicating arrangement, and then we're off to the races. And indeed, for something like 2 billion years, there was only single cellular life. It took a very long time going from the first cells, the first living things on Earth, to the to multicellular life, or to eukaryotic life, the sort of life that we are, which again is a remarkable story that someone else should give 8. I would love to attend 8 Compton lectures on the beginning of eukaryotes. It turns out, if you didn't know this, right, our cells, eukaryotic cells, came about because 2 different types, at some point, some 2 billion years ago, 2 different types of single-celled organisms. One of them tried to consume the other and failed, and instead sort of took the other into itself, a process known as symbiogenesis. This is the archaea, one of the early branches of single-celled organisms, becoming the nuclei that we have in our cells. Now nuclei used by the biologists means sort of the region in our cells where our DNA lives, which is separated in our cells from the rest of them, the rest of the cell, precisely because it started as some different type of organism. Okay, anyway, I'm getting distracted, but once that had happened, more complicated life occurred. Well, again, it took hundreds of millions of years. At some point, some cells evolved that produced oxygen and oxygenated the atmosphere. Eventually, multicellular things came about some 500 million or so years ago. Here we are, some 500 or so million years ago, we have the beginnings of animals, the sorts of creatures we are, evolving in the oceans. We were relatively late in leaving the oceans, only some 400 million years ago or so. Our ancestors, tetrapods, left the oceans. Something like 300 million years ago, mammals first evolved. If you have a pet cat or dog, you share a common ancestor with them. Something like 100 million years ago. Is that here? Something like around here, you had a common ancestor with your pet cat or dog. We only differentiated from chimpanzees, our closest living relative, something like 5 million years ago. And all of us in this room share a common ancestor, something like 150,000 years ago. And in fact, good. It is really remarkably, we've discovered in recent years that it is only very recently that we are the only humans on the planet. We have discovered now other types of humans, Neanderthals you've probably heard of. In recent years, things like Denisovans, Homo floresiensis. There were different groups of, the terminology is archaic humans, but they lived only, they only died out something like 30, 50,000 years ago. We were living with them for a very long time. And in fact, if your origins are in sub-Saharan Africa, you are the most human among us in some sense. For the rest of us, our ancestors, after leaving Africa, met these other groups of humans, perhaps the results of even earlier dispersals out of Africa, met the Neanderthals and met Denisovans if you come from Southeast Asia. Unfortunately, the evidence seems to point to us killing them, driving them out of existence. But maybe it won't surprise you that in addition, we interbred with them. And so unless any of us who does not come from sub-Saharan Africa has an appreciable amount of our genome that comes from relatives who were Neanderthals, ancestors who were Neanderthals or Denisovans. It's a remarkable story. I'm sorry I don't have more time to go into it. Thank you for putting up with this hodgepodge of things today. Next, because I wanted to get to, next time we will get back to particle physics and indeed go on to some things that are a topic of current research, are more close to what I actually work on. We're going to go beyond the standard models of particle physics and cosmology, beyond what we've currently observationally seen, and think about what could happen at even smaller distances, something like grand unification of all of our different forces eventually becoming one. Maybe I'll talk about baryogenesis, how we think it happened, that in the beginning there was this slight difference of matter and antimatter. Maybe depending on what, I'd be interested in what you guys would like to hear about. Could go into topics like supersymmetry or the possibility that there are extra dimensions. But we'll hopefully, it will certainly be a fun mix of some theoretical ideas that we think we have very good reason to expect will be there, but we haven't seen observationally yet. Okay, thank you. I'll see you next week.